we have kind of covered this topic via these subtopics. We looked at framework, the limits in the various limits of the parameter space, T mu V space, and then eventually the QCD phase diagram, which is the most popular diagram in our community, and the features of which we are all after, right? So today I would like to start on looking at this QCD thermodynamics from the experimental point of view, like how do we access? So if at all, so of course you could ask whether at all a equilibrium, such a thermodynamic and chemical equilibrium is set up or not, right? You could ask that. That's a good question. Or you could also ask if that state is there, okay, if a thermodynamic and chemical equilibrium state is set up, can I measure uh, the that state's property, right? So what is the thermodynamic property of that state? In fact, so in other words, can I access this temperature, this chemical potential, right? So we assume, so of course we are not proving equilibrium, we assume equilibrium and then ask what is the property of that equilibrium state, right? So, so to do that, what we typically look at is phase space integrated observables, right? Now, in heavy ion, of course, by phase space, usually we mean x comma p, right? But in heavy ion, I mean, the x in the firewall, that is out of question. We don't measure that. Our entire, I mean, by the heavy ion observable phase space, when we say it's only the momentum space, right? So if I integrate, however, I mean, some momentum when I'm observing, right? Px, py, pz, say, from the spatial points of the fireball, I don't know, suppose this is my cylindrical fireball, right? That point could have come from here, could have come from here, could have come from here, anywhere, right? Because we don't know. We are just measuring the momentum space, right? So in that sense, you could say that the space is also integrated, right? So, so, so we can never do a spatial differential observable, right? All we can do is a momentum differential observable. But having said that, the spatial is already integrated in that, right? So we are good to say, okay, it's a phase space integrated observable, right? So once we integrate out the momentum and so the momentum space or the phase space, okay, we typically have observables, say yields, okay. Yields have been in the business for a long time, and recently, not very recently, but still recent in terms of the progress of the field, uh, we are also dealing with fluctuations, okay. So mean has been there for quite some time, and lately we are also dealing with fluctuations. So usually when fluctuations, people talk of conserved charges, but you could ask, why not hadron yields? Are they useful? Are they not useful? So that's different question. So in fact, when you want to calculate the fluctuation of a conserved charge, you have to break it down in terms of fluctuation of hadron yields, right? Because this is what you are measuring, and then you take suitable combination to construct the conserved charge, right? So whatever it is, the yield or the conserved charge, but at the end of the day, these are all phase space integrated observables, right? And when we do that, what we eventually get is we establish the freeze out, right? We establish freeze out, and we do it within the framework of HRG, which we already discussed here, right? This has been for a long time, and it has been a very, very phenomenologically successful program. And lately, even a first principle method like lattice QCD has also joined this effort, and we will discuss how by comparing measurements of conserved fluctuations of conserved charges, one can now do a direct comparison between something as first principle as possible, like lattice QCD and experiments, right? And in the end, we basically establish the result. Okay, let's get going. So contact with experiments via phase-space integrated observables, and first we will discuss the mean hadron yields. Okay. So this is a plot that I took from this nice article. What has been done here is at various beam energies, right? Starting right from RHIC 200 GeV to all the way down to AGS energies of a few GeV, right? This n part 350, because the different experiments have different centralities. So somehow they have done a slight bit of scaling to ensure that you are looking at a same system. That means you are looking more or less at the same centrality. So the n part is kind of similar, because only then it makes sense to compare the yields of different experiments, right? So that's it, they have done somehow. Okay, so a little bit modeling has gone in that sense, but otherwise this is data. Okay, so what is the first thing that we notice? So the first thing, we most likely notice is that let's start from low beam energies, and you see there is a rapid rise, right? There is a rapid rise of most of the species, right? So the yields rise rapidly for small beam energy. Okay, and then beyond about 20 GeV or so, you see the mesons, like the pions here and the kaons here, right? Their rise is kind of gentle, right? Their rise is kind of gentle. And on the other hand, the antibaryons, right? So you have the antiproton here. Then you have the anti-lambda here, right? This comparatively still rises quite fast, right? So the mesons rise gently, the antiprotons, the antibaryons still seem to rise quite fast. And in contrary to this overall general trend is our proton and lambda, right? These guys, instead of increasing with beam energy, you see, for example, the proton, which is the open plus green symbol, it's falling, right? And then, so initially it's rapidly falling, and then there is a gentle thing, right? And what about the lambda? Yes. So the lambda here, there is a certain rise, and then again a certain fall, and then again like this, right? So lambda seems to be more complicated. Well, good. So these are the trends that we start noticing, right? And then, in terms of our thermodynamic parameters, T and mu B, now it should start ringing a bell in your head that, yeah, maybe I come to this expression and make my comment. So the phase space, so these are all phase space integrated, right? This is just d and dy. Well, not really. So only the rapidity, in the rapidity direction, maybe there is some, it's a mid rapidity calculation or observation. So say 0.5 or I don't know, 1, whatever, up to the experiment, right? So these are, so in that sense, the PZ is not kind of integrated, right? There is a cut in the rapidities, but at least the transverse component, it's all integrated, PT integrated. Okay. So these phase-space integrated hadron yields, they can provide information about the thermodynamic conditions, okay, of what, right? So if once you assume, so if you assume that the fireball is always perfectly in thermal and chemical equilibrium, right? Then the only thing that you can hope to access, right? The only thermodynamic state that you can hope to access is the surface of last scattering, right? I mean, the last surface where this condition is true, and after which the collisions between the constituents become very less so that it cannot keep up with the expansion of the fireball, and hence the condition of thermodynamic and chemical equilibrium breaks down, right? And you lose this thermodynamic state, right? So, so the only state that you can access is that last time when this was true. Why you cannot access the state which was just prior to that, or little prior to that? Because you are already thinking that it is in complete thermal and chemical equilibrium, right? Once it is in complete thermal and chemical equilibrium, that's the maximum entropy state, okay? It doesn't have any history, I mean, any memory of the past, okay? So it is just at that temperature and that chemical potential. You cannot access any previous history to it, right? So does that mean that in heavy ion we don't measure? I mean, we don't make a comment on anything else other than freeze out? No, we do that, but for that we have to look at phase space differential observables, right? Which we will discuss in the next lecture, maybe tomorrow. But for today, we are discussing phase space integrated, and there you are the only surface, the only state that you can hope to access is this surface of last scattering, which in other ways is, I mean, in more common parlance, it is known as this freeze out, right? So as we saw, there is good agreement between LQCD and HRG, okay, where the hadron states are there. And if you assume that the freeze out is freeze out of hadrons, that means the fireball is in such thermodynamic state that the degrees of freedoms are hadrons and resonances, colorless states, and not quarks and gluons, right? So then this then HRG, of course, is a very good model to access it, right? That means what you are assuming, or what you're hoping, is that it's somewhere here, right, and not here, right? Because here we know that the HRG results will break down, right? Because here this non-interacting gas results will break down, for example, through this plot that we saw yesterday, right? Because the HRG is this one and it is all zero, whereas you expect already non-zero this quantity to become. So it should be somewhere here. So, and once it is somewhere there, then of course we know that HRG is a very good description. And the the benefit what you get by that is then you can directly compare the yields, okay, with your measured yields in the experiment. So in the HRG model, you can compute the yields by your standard thermodynamic relation, right? For every species, okay, suppose the ith species yield you want to compute, you have to take a derivative with the corresponding chemical potential mu I, del mu I. Within the HRG framework, each hadron species is like a conserved charge, okay? And that's why you can do this. And that's why lattice QCD cannot do this, because in QCD, in the real QCD, the only conserved charges are net baryon, net charge, and net strangeness. Okay, each hadron yield, I mean, those are not conserved charges. But it happens so that in this, if the temperatures are small enough, right, then it's a good approximation to approximately consider that even your hadron yields are kind of conserved, right? Because the temperatures are considerably low that you don't produce now. Okay. So once you have this expression, now here you see there is this temperature, and this temperature enters the expression for the yield, no matter what is this species, right? Whether it is a meson or a baryon, antibaryon, whatever it is, this temperature is always there, right? And the other thing, this chemical potential mu I, okay, this, well, I didn't write down here, the mu I is taken to be, maybe I can write here, mu I is mu B times Bi, which is a baryon number of that species, mu Q times Qi plus mu S times Si, right? So then it matters whether the yield, are you talking of the yield of a pion, right? If you are talking of the yield of a pion, for example, then this is 0, right? Then this is 0, right? Only thing is this, okay? And typically the values that we obtain, mu B is the most important because that's the largest. These mu Q and mu S, okay, are much, much smaller, order of magnitude smaller, okay? So if you're talking, however, of a proton, so then it gets a very large contribution from this mu B, right? So this observation that you are seeing here, that the pion is varying in one way and the proton is varying in the another way. Now, if you correlate with this thing model, and if you assume that this model could be giving a good description of this, what it implies is the temperature, right? The temperature and the mu B, they should be varying differently, right? And we will come. So only then you can manage to explain such different trends of a different species, right? Of pion from proton, right? Because the mu B doesn't enter the pion, right? So that I already said some of the things anticipating the slides to come. But anyhow, so this is the program that you have the yield expression within this HRG model, and you experimentally measure these yields. So you go ahead and fit this model where the yields are function of this temperature and chemical potential, and you try to simultaneously fit at a given beam energy, okay, as many hadron species as possible, and try to see whether you can come up with a good overall description or not. If you come up with a nice description with a relatively small chi-square over NDF, say, then you say uh, that, okay, this model seems to describe this fairly well, and if our assumption of a thermodynamic and chemical equilibrium state is right, then that state must be at this temperature and this chemical potential, which manages to capture all these yields simultaneously, right? So that's the argument. And this program has been carried out over the years across various beam energies. And here I particularly show one example at root S 200 GeV. And you have so many particle ratios.
Hello, sir.
Hi.
Can I ask? Yeah.
Yeah.
This is
What is
Dukhishyam.
your name? Okay, Dukhishyam.
Sir, this is Dukhishyam. Yeah.
Yeah, go ahead.
Sir, my question in the previous slide, how can I understand the yield difference between the species. If you look the pion, pi plus, pi minus as function of energy, that difference is not significant. But in
Yeah.
case of you looking the K plus and K minus as increasing the central mass energy, the K-on yield is higher than the K minus.
Right.
But the LHC energy, higher energy, the difference is
Yeah.
close. And
Yeah.
similar argument is also hold for lambda, lambda and lambda bar.
Exactly. Exactly.
How we can understand this? It is
So you
related.
have done all the hard work. You have identified. Now you think in terms of these, right? So what do you think? Think who is
Uh,
what? How they are charged? Now tell.
uh, the for
So you
K-on, the
said,
difference may be related to some strange content.
yeah, exactly,
Maybe
right? Yeah, go ahead.
I think there may be some production mechanism, but that may be affect because K plus is higher yield. Maybe the quark content is US part.
Yeah.
But
So one thing is here, we are not trying to understand things from microscopically, right? We are trying to understand from the thermodynamically, right? So you just think in terms of temperature and chemical potential, okay? And as I said, see, the temperature is the same temperature applies to everyone, right? But the chemical potential is selective, right? Species selective. For example, if it is a kaon, then it will just have this, okay? Also this mu q because it is k plus and k minus. But lambda, for example, will have mu b and mu s both, right?
Sandeep, can I
So,
just
yes, sir.
hello.
yeah, Sandeep,
Yes, yes, sir. I can hear.
if I understand correctly, the
Yeah,
yield of K plus and K minus are significantly different at lower energy, right? Not
yeah,
at
Yes, yes, sir.
higher energy.
yeah, yeah.
Sure.
So let me just maybe show one more slide and then we again come back to this. So that's a very good, important observation that at the highest energies, you see all the differences are trying to go away, right? And it's only at low energies that, these splittings are happening. So that's again another hint, right? So let me just come one more slide and again we will go back to it. Um, so here I was just telling about this program. You have various yield ratios. You can also do with the yield itself. The added benefit is if you do with the yield, you can also extract the volume, for example, the effective volume. When you're doing with the ratio, the volumes could be getting cancelled out. That could be beneficial in one some sense. Then you are only like kind of, you want to be only sensitive to temperature and mu b. You don't want uncertainties over volume to hinder, to interfere your extraction of T and mu b. So you could be working with ratios, or you say no, I want volume also. I think is an important thing. I want to know that. Then you could straight away fit simultaneously T mu b v. But then you have one more free parameter, and then these chi-square things can look more complicated, right? Contours. So this is a typically thing, and this is some typical values with chi-square. So here there are two fits they had done. So first of all, these resonances have not been included in these fits, in both the fits. And moreover, in the one with a smaller chi-square over NDF, they did not fit, if I remember correctly, phi by k and antiproton by pi. Okay. Somehow they thought, okay, maybe if I just, so they may have played around and seen key, okay, if you remove these and just take the others, then you get a more nicer fit. But anyway, I mean, up to certain MEVs, but broadly it's the kind of the similar uh, ballpark, right? The temperature and mu. So of course there will be systematics, but overall you can do a quite a good robust estimate. Okay,
So,
so this, yeah,
Sandeep,
there was, yeah,
So what is the? Can you go to the previous slide, please? The one
Uh,
just now. No, no, the one with contours. Yeah.
yeah,
Here, so here the these contours are what? The constant chi-square contours.
yeah. I think these must be constant chi-square contours. Yeah,
Okay.
and then plus one, plus one, plus one. It could be.
Chi-square
Yeah.
plus one. Chi-square
Huh.
means plus two. Okay.
Yeah, yeah, yeah. So this is because it gives you an estimate of your uncertainty
Right.
over the parameter,
Correct.
or estimate of your model parameter. Right. And so this now you can do at all the beam energies. Okay. And again, keep extracting this T mu B, T mu B. This has been done by many people for a long time. And so these I have taken particularly results from here. And you see, this is the kind of variation that you are getting for temperature. You see a rapid rise up to about 10 or 20 GeV, and then there is kind of saturation, right? At around, okay, 150 to 160 MeV. Okay. And for the mu B, on the other hand, the trend is opposite, right? While the temperature is rising, the mu B is rapidly falling, and then it's kind of goes to zero at very high energies. Okay. Here we have only up to RHIC, top RHIC, that was then in 2005. Now a more recent plot, you would also get LHC, and LHC is within error bar zero mu B. Okay. However, the temperature is still about 155, even a little lower, depending on model, exact model details, what you are implementing. Okay. And this is a volume parameter. Again, so the volume shows also a very interesting trend. All these things are more or less non-monotonic, the temperature and mu B. However, the volume you see kind of shows a non-monotonic trend, and there is a minimum around 10 GeV, right? And to compare with the HPT volume, also these have been shown here, although the estimates from HPT are very different because it's from a different observable, and these are from yields, and so they are expected to be different. So this is not bad that two different estimates are giving you different estimates of volume, because these are different physics. Okay. And so you can always parameterize these things which are shown here through these solid lines, right? And one typical parameterization is possible is this. However, it's not unique. You could parameterize in many other ways. Different groups follow their own parameterization. And then these curves are then become very important, vital tools from the point of view of phenomenology, and you could then go on to compute many other quantities and try to predict or compare with your observables, right? So now that you get this trend, right, you can now come back to this plot, and you see, first of all, you can now understand that this proton is falling and then staying constant, mainly because of this baryon chemical potential, right, which is falling and then staying constant. Those guys which are not protons, which are not baryons, right? So mesons and antibaryons, right? They are all rising, right, very fast here. And so mesons are rising because the temperature is rising. Antibaryons are rising because the temperature is rising, as well as the baryon chemical potential is falling, right? So both of these factors favor the rise in the antibaryon. You see, even beyond 10 GeV, right, this temperature is almost flat, and so the mesons are almost flat. However, the antibaryons, you see, as I said, they still seem to rise, right? And that's because the mu B still falls considerably, right? So the falling in mu b drives the still the relatively rapid rise in the antibaryons, right? So of course it's a fit. So I mean, it's not a saying, oh, because of this is happening. But this is how in the HRG model you can understand the yields. Within the framework of the HRG model, this is how we can understand the variation of the yields. So it's the variation of this thermodynamic state at the chemical, at the freeze out. Okay. Okay, great. And so, and those little splits that you were saying about, talking about, say pi plus pi minus split, okay, and k plus k minus. So the splits are happening because of this mu q, right? Because pi plus and pi minus, everything is same except their electric charge. Now electric charge means mu q is there. Now, and for k plus k minus, again, everything is same except the charge as well as the strangeness, right? So for kaons, both mu q and mu s are playing a role. For pions, only mu q is playing a role. And from these extracted values, what we see is that largest is mu b, and then is mu s, and then is mu q. Okay. And typically, if this is 100, then this is 10, and this is like 1 MeV. Okay. So you see there is a larger split in the kaons, right? K plus and K minus than in the pions, right? Because the mu q is much smaller, but the mu s is quite large. So there is a larger split there. And of course, as you go to lower energy, the split becomes larger and larger uh, because these chemical potentials, all of these chemical potentials increase as you go to lower energy. And that rise is driven by the rise in this mu b, which physically is happening for what is known as the baryon stopping, right? More as you go to lower energy, at the time of collision, the baryon transparency decreases, more baryons or more participants get deposited in the mid rapidity region itself. And so the fireball carries larger net baryon charge. Once it carries larger net baryon charge, okay, one can do some uh, uh, small calculations, not very hard, that if you put those constraints that we discussed, net strain is 0 and net B by net Q to be 2.5, you can see the fact that there is large net baryon would also imply so that there is large mu B, and which will then imply that there is large mu S and large mu Q. Okay, and so all these splittings start happening at lower energies. So that's how we understand within the framework of uh, hadron resonance gas this thing, right? And so going back to our like QCD phase diagram, then so I mean, a few classes back, we had put this curve, which was the freeze out, right? And so what all things we can put, we should look out for on the QCD phase diagram. And so now we can also include this freeze out curve, right? Because this T and mu B that you get, you can collect them and start plotting them here as per beam energy, right? So, and that also tells us, I had mentioned that we have T mu B here, how we could also plot this root S, right? Where was the connection? So now this is the connection, right? At a given root S, you are finding a particular mu B and T, right? So at a given, so you are finding, suppose that is that T and mu B that you find, okay? And then you come here and that's the root S, right? So this is how you try to identify a given beam energy with a given T mu B point on the QCD phase diagram, which is the freeze out point, okay? Yeah, that's where the firewall kind of beyond which the fireball, so the fireball is always cooling, it is rapidly expanding. So you could think like it's cooling down, but of course there is no more thermodynamic state here because this is the surface of glass scattering. So there could be here, right? But those we are unable to access via this kind of an analysis where we have integrated out all the momentum thing, right? For that we should look for differential thing, okay, which will come later. So we at least then establish the freeze out, okay. And so this is with the yields, and one could do the same story now with the fluctuations of conserved charges. Although in the community, this observable fluctuations of conserved charges was first introduced or spoken of in the context of trying to locate the QCD critical point, right? Because the idea is close to the critical point, the correlation length diverges, okay, and then what happens is the in a thermodynamic ensemble, the fluctuations which are otherwise like grand canonical thermal fluctuations, when the correlation length is much smaller than your system size, but once you are nearing a critical point, the correlations length diverges, they can become as large as the system size. And then the fluctuations will no more act like thermal, right? So deviation from expected thermal fluctuation in the observed fluctuations of conserved charges would signify that there is some non-thermal thing that is happening. And we hope that is critical point. But of course, there are a lot of complications, right? Something thermal, it is easy, okay, just the Boltzmann law. But something non-thermal, now it can become non-thermal due to various reasons, right? So various background, hence there is a lot of discussion. And of course, it's a tough and challenging task. But nevertheless, this is a very important signal to look for such non-thermal behavior, and the prime suspect could be then a QCD critical point. But very soon, people also understood that it is important to also establish. So because you want to search the critical point, you want to say you want to understand deviation from thermal behavior, right? But then one thing we know for sure is that the entire phase diagram is not critical, right? So critical is a very probably small region or something. However, most of the regions should be thermal, I mean non-critical, and hence fluctuations, if you are having a grand canonical ensemble, okay, then the fluctuations better be thermal, right? So which means you should be able to establish the freeze out curve by also measuring the thermal fluctuations of the conserved charges, because these fluctuations of conserved charges, they should be also messenger of the thermal state of the fireball, right? And hence people very soon realize that before even establishing, trying to search for critical point, let's establish that we are these fluctuations make sense and all these things as per our expectations, and hence they should be thermal like, right? Where you don't expect critical point. For example, somewhere here, say lattice, say LHC, or say top RHIC, right? And then of course you do beam energy scan and you hope that you encounter something which is non-thermal, whose origin you cannot explain, and then the only candidate would be a critical point. Okay, so fluctuations of conserved charges from theory, for example, you could look at electric charge fluctuation. Of course, if you are looking at the entire fireball, nothing fluctuates, right? Because by definition, it's a conserved charge. So as long as in the initial state you are injecting same amount of net charge in every event, okay, So suppose somehow you ensure that, then in all those events, net charge will be same, right? The total net charge. So the idea is you should look at a small sub fireball, right? And that we do by various these acceptance cut, and then in that small region, right, the charge at from event to event could be different, right? And that fluctuation from its mean value should be precisely given by what you expect from a grand canonical ensemble fluctuation, right? And these are standard textbook material. uh, for example, specific heat, we say, right, temperature fluctuation or energy fluctuation. Likewise here, it's a different conserved quantity. It's say baryon. QCD has net baryon, net charge, net strangeness. So you could be looking at any of these conserved charge, for example, and their fluctuation. um, for example, you could look at the electric charge, and these are the susceptibilities which we had already defined earlier, and they are connected to these experimentally measurable things, right, via these relations. So from experiments, from the uh, moments, mean, variance, kurtosis, skewness, kurtosis, right? Again, one can connect these cumulants. So which means from theory, we have these quantities, from experiments, we have these quantities, and this is the main quantity which is the input to both, and hence you can relate them, you can find relations, and then you can, because in the theory, these quantities depend on the thermodynamic state. So by measuring these quantities at a given beam energy, say, and then fitting it to them, right, you can extract what is this T mu b, right? So the program that you did with yield, you can also do with fluctuation of conserved charge. And this is quite straightforward to do, for example, in a framework like HRG. And this has been done. I just took a result, for example, from our analysis here. And so there are some certain systematics here, depending on in the HRG what particles you are taking. There is a little variations, right? And this other thing is, this is from the yields. So these things are from the yield. And this BQ, so these purple things, so these things, these are from the conserved charge fluctuations, okay? And what we have here, so this is the extraction of the temperature, and this is the extraction of mu b by T. And what we get here is, one thing to notice is that there is a, across the beam energies, right, there is a systematic uh, smaller temperature that you seem to extract, okay, when you use fluctuation of conserved charges compared to when you use the mean of these hadron yields, right? Right now, let's just have it as an observation and go ahead to look at also what lattice can do, because uh, once we talk of conserved charge, then lattice can also compute these things, and these are first principle calculations and hence important to look at. However, lattice, remember these susceptibilities, they have this VT cube, okay, which are like, for the lattice case, these are like the phase space volume. And often we are just interested in the T and mu b, which are like more like intensive, uh, thermodynamically intensive quantities. So to make them intensive quantities and not extensive, we can take suitable ratios, right, and cancel out these factors. Otherwise, uncertainty over them could hamper our extraction. More important, this is more important for framework like lattice, and hence what they do, they take suitable ratios so that that VT cube dependence cancel out, and what you have is something which is only dependent on T and mu B, right? And so you can measure this in the experiment, and on the lattice you can measure this, and then try to correlate this to find what is the T and mu. So this is typically known as RQ12, right? This is one derivative and this is two derivatives, so it's a 1, 2, and this is RQ31, this is three derivative, this is one derivative. So the ratios, so this program has begun and so far has been quite successful. For example, this is a plot for 62.4 GeV. This where in the left hand side you see the star measurement of R RQ31. So this quantity here, RQ31, that means this is what you have measured. And right now, I think there is a bit large error bar, which means from the lattice point of view, these are the lattice calculations, and they have done it with varying temperature at different mu b by t, right? So what you first of all, what we notice is that all these different mu b by t seems to fall on each other, right? So which means that this is quite insensitive to this mu b by t that you use, right? However, it is quite sensitive to temperature, if not here, but here at least there is quite a large variation, right? And that's exactly what they have managed to do. Once you put this thing, what this is saying from first principle is that the freeze out temperature is at least less than 155 MeV, right? This is an important statement. Now, as soon as you say less than 155, it's very good for HRG people, right? Because, oh, then we do quite a good description there. So as long as it is not here, okay, HRG people are happy, okay? So, but here, then so long, whatever we were doing with yields, it makes sense. It's not completely that you can throw it to the dustbin. Okay, and good. So, but you cannot say anything about the mu b by t because they are on top of each other. And now, fortunately, you have this other observable, which is RQ12, and you see this guy RQ12 with mu b, right? This is the, it is having this large kind of variation, right? Of course, as you go in larger mu b, you see the error or the uncertainty in the estimation of RQ12 increases because these lattice methods are best suited for 0 mu b, and then they tend to become more and more uncertain as you rise, uh, as you go to higher and higher mu b, right? And then this is done for a typically 150 MeV lattice temperature, because already from HRG we know that this at up to quite a large mu b, this temperature is hardly changing, right? So you could just keep, because this curvature is so small, so you could just keep the temperature some value. So they have kept just 150, for example, here, and then they just change the mu b and they compare with the experiments here, right? And so this is the mu b they extract for different beam energies, right? As you go to lower and lower beam energies, you get larger and larger baryon chemical potential. Of course, the error in this estimate becomes larger, mainly because this band is broadening up. And here with this black arrow is the estimate from HRG. So at least things are consistent within reasonable range, right? So Good. So this program is good. So we can now put them all together, mean and higher moments. I took this plot from Science's latest review. So you have the mean, so temperature and newbie. So these star ones are the from the mean, and the higher order moments are these blue box. And again, you see, typically, systematically, there is a from the higher order moments, it seems you are getting a few MeV lower values as compared to the mean. But at least at the 0th level, we have tried to look at this freeze out from various angles, and more or less there is a region on which all the methods are falling. Of course, there are a lot of details, very interesting and exciting ones, which are good because they give us ability to even probe and dissect this thing more and more and refine the description and our understanding. But at the 0th level, this is a very important and good understanding in my view. So, so note what I just mentioned here, that the higher order estimates of freeze out temperature are systematically lower. And so one example of detailed question that one could ask is, does it imply mean and higher moments do not freeze out together? Or what is, yeah. So this is, for example, one question that you could ask, for example, right? Because um, from the yields, it's more like the chemical freeze out, right, where the chemical composition has frozen, but there could be still some elastic scatterings that are happening. And if your acceptance is something, right, um, due to elastic scattering, you could be uh, and also there is expansion. With time, it is only expanding, so there could be some loss in particles and so on in that same acceptance, right? And so that could effectively mean from the fluctuations, it could look like as though the temperature is lower. But anyway, so these are, of course, debates and ongoing topics of ongoing research. For a 0th statement, I think this is quite a robust estimate that we have now. Okay, so I think I will stop here. We are already, and so we have now covered till here. And so the next lecture, we will look at contact with experiments via phase-space differential observables. So any questions we have? No questions?
Sandeep, can I ask one question? Here is Rajendra.
Yeah, hi Rajendra. Yeah, go ahead.
Yes. In your, I think, 3-4 slides back, somewhere you have shown that dV deta, the volume, that there is a dip.
Yeah.
Yes, yes. I do not understand how this dip can be explained. Can you repeat once more?
Yeah, so I am, so in this whole thing, you see, I have presented them like just extracted fit parameters, right? So I am not, I don't think we have tried to, I mean, we can explain why this is like this, right? Why this is like this, and why this is like this, right? That is even like a next question. So,
Okay.
so this is, I'm just putting like, okay, if you fit, this is what you get in that. So very like simple.
Okay.
So usually this one people will say baryon stopping, but for me that's another name. But what is it? So that I don't think we understand that well.
Okay, thank you.
Yeah, but yeah. So I think these are questions that we keep thinking. You know, there is a lot of discussion on the critical point being somewhere here or there. Now, all those things, are they affecting the dynamics in any way? I mean, one has to think. Right?
Oh, so this is basically coming from fitting parameters.
Yeah, this is just
Hmm.
fitting this thing, right? Fitting this yield
Mhm.
to this experimental yield.
And in your previous slide, I'm curious. No, yes, this one. So yes, at SPS and AGS energy, let's say, if I compare proton and antiproton, then they have completely different trend. So
Yeah.
that is observable. And is there, I mean, any dynamic that I can imagine that this would be the reason that why antiproton is?
So that one is like, once you, if you believe now this, then it is so, just by making just if you believe ki, okay, mu b is increasing,
Yes,
then you expect proton and antiproton to go oppositely, right? Because
yes.
proton is like e to the power mu b by t. Uh,
Mhm.
so like it is like e to the power mu b by t, whereas, so this is proton, whereas antiproton is like e to the power minus mu b by t, right?
Mhm.
Because the baryon number is -1.
Mhm. Mhm.
And so one goes, the larger the baryon chemical potential, proton is enhanced, but antiproton is suppressed. So is anti-lambda.
Mhm. But just if I want to think in point of view mechanics of the dynamic, then what could be the reason?
No, so that's, so somehow there has to be some mechanics for this baryon stopping, right? As you go to lower beam energy, somehow the incoming nucleons, they are strongly, they lose their rapidity and they are mostly deposited at mid rapidity. And then if they, so that's all that you have to, one has to understand. Once you understand that, then we have a thermodynamic, I mean, fireball which has a large mu b. If you have large mu b, then these can be understood, right? Because proton should be large, antiproton
Yes.
should be less.
Mhm.
So that initial condition needs to be understood, how that baryon stopping is happening, right?
Yes. Yes.
Because this is important, because in our search of critical point, we are looking at proton fluctuation and so on. So we need to understand how you are stopping the, I mean, we say we are looking at net baryon fluctuation. So it is very important that we understand how we are injecting net baryon into the fireball. And that's the baryon stopping mechanism, right?
Thank you.
Because you are looking at event by event fluctuation in that net baryon. So it's event by event, how much net baryon are you injecting in the fireball? That is like a background, right? Because if you, in the initial condition itself, if you fluctuate the net baryon in some way, and that's a completely a non-thermal fluctuation. We should not look at that and think we have found the critical point. Then it will be problem, right? Yeah. Okay. Any more questions do we have?
Sir, my question is how we extract this dv by dy, which experimental observables, we can obtain this dV by dy.
So this d and dy, these yields.
I mean, how it is related to d and dy? It is simply cube of.
So this is the formula that I have written here, right? So this you should not do. So this is like number density, but this is number. So in this formula there should be this v, and because you are doing d and dy, so this is like dv dy. So that parameter is extracted, also fitting parameter, right? So you have a t, you have a mu v, and you have this dv dy. Right?
Yes, sir.
Because this n here is like d and dy. So this v has to go here, right? So this is like a dv dy. Which you have
Like
to fit and find out.
simply spectra, we fit the we can obtain from d and dy. Then the transverse mountain spectra, if you obtain the d and dy, then how we convert this dv by dy, or otherwise we can fit this.
From spectra, you find this d and dy, right?
Yes.
And now this is you are comparing with a model, and in that model, then dv dy, t and mu v are the parameters. So via this formula.
Can I make a comment?
Yeah.
I think what we measure in experiment is this triple differential invariant cross section. It's d2n by d2pt dy.
Yeah.
They just integrate over the transverse direction, you integrate it over the pt, entire pt coverage. What you are left with is your d and dy in your experiment.
Yeah.
They, as you have told just right now, as you have told, that you can fit this formula, or if in one can write instead of E, one can write it mt cos hyperbolic y. Also the phase space integral, the momentum integral, one can separately factor it out in terms of pt and d2pt and dy, and then again integrate. If you integrate it over the pt, what you are left with the y dependence.